Thanks a lot. And well, first, of course, I want to thank the organizers for giving me the opportunity to be here in Paris, not really today to celebrate a great colleague of mine, a colleague of 14 years here at USC. And even more importantly than that, I have to say a close friend of mine. I don't have many papers with Hubert. In fact, I believe I got just one. For whatever reason, but I have, I've had many conversations, many dinners, many drinks, and I won't go for. I'm not going to tell you guys any joke or showing any picture of Hubert, but make no mistake, this doesn't mean that I don't have jokes and pictures. They are just not probably appropriate for such a distinguished meeting. So I will start my talk. And I suppose I have 40 minutes. We're running late in the schedule, but can I still go for 40 minutes? Can you guys actually hear me? Whoops.
Minutes with questions.
I don't have any feedback. Can you guys hear me?
40 minutes with questions.
Okay. You can hear me, right? Because I have very little feedback, I have to say.
Yeah, we can hear you.
Okay, very good. Thanks a lot. So what I want to tell you today is basically sharing some of the work that I've done recently with my students, Yorgos Stiliaris and Mitterrand, on information scrambling and over bipartitions, and how those connect to equilibration dynamics, entropy, production, and typicality in many body systems. So the broad subject we are going to talk about is quantum scrambling. By quantum scrambling, I just mean the ability that quantum dynamics has to spread across many degrees of freedom information that was at time t equals 0 localized in a subsystem. And there are many different ways of doing that. One way that has become fairly popular recently is to resort to the so-called out-of-time order correlation function, or OTOCs. And one way of thinking about these OTOCs here is that, can you guys see the pointer of my mouse? Because I can't. Okay, I think there's some time delay here. Anyhow, so information scrambling is typically characterized, or sometimes maybe characterized, by the growth in time of commutators, or if you wish, equivalently by the decay of correlation functions. So you can start from some operator W, say an observable, even though we're going to pick those W's, and even V being unitary operators. And then you actually, can you guys see me? I made it smaller in order to see my pointer. Actually, I don't have much feedback. Maybe there's a time lag here.
It's way too small for reading the equations.
Is it okay? Is it still okay?
It's way too small.
Oh, it's way too small. Okay. Good. Okay, I won't see my pointer though in this way, but maybe you do. Okay, good. So what I'm going to consider two local operators, V and W, and I'm going to evolve one of them, V of T, being here just the Heisenberg evolution of the local operator V. And I'm going to see how the strength of the commutator with some other operator W that is local in some other subsystem of my overall quantum system grows in time, or what is the dynamics of this commutator strength. And this commutator strength is defined through the Hilbert-Schmidt norm. When you see a lower index 2, it just means that I'm referring to the standard Hilbert-Schmidt norm of the operator. And well, equivalently, you can write this expression here that as 1 minus this correlation function, a 4-point correlation function. That is what is usually referred to the OTOC, namely out of time order correlation function. So let me share what is the setup here. It's fairly simple. I got a Hilbert space H over here, and it's a bipartite system. Namely, it's made out of two subsystems that carry labels A and B that have dimension dA and dB respectively. And what I'm going to do, I'm going to pick my V being a local operator in A and W being a local operator in the subsystem B. So I got a bipartition. I'm starting from some operator localized over here. I let the operator Heisenberg evolve in time, and I see how the commutator, the commutator with something that was initially localized in the subsystem B goes in time. So the question here is, what does the commutator quantify for a generic choices of WA and WB? Okay, for example, I could think of WA and WB being generic random unitary local operators. Namely, I could draw them from the uniform hard measure over the corresponding groups. And I'm gonna ask myself, what is this, what is the average, what is the expectation over all possible random choices on V and W of this quantity here? This quantity, in this way, resorted to typicality, the fact that the deviation from the average behavior becomes extremely unlikely. In fact, exponentially unlikely in high dimension is going to capture the typical behavior of this quantity for random unitaries. Okay, I'll move on. Is there any question here? If you have, please stop me. This would help in filling. Okay, I'll skip the summary here. I'll try to keep this nice and easy. Okay, so the first result is that this average over random hard unitaries localized in system A and system B can be actually performed and gives rise to this formula here that you see on the right. Again, I don't see my mouse pointer, so I don't see whether I'm pointing at it or not. But anyhow, is 1 minus d squared the trace of the swap operators between the partial swap operators between two copies of the Hilbert space. So the Hilbert space gets doubled. So this is why I have the tensor, the second tensor power of my dynamics. U of t, of course, is my evolution operator. And I have this expression here that may, well, first, it's nice that you can actually perform such an average, but it is remarkable the result. Because not just because it sounds, or at least it looks at for me, kind of an elegant result, but because this turns out to be a formula that in some other field has been known for a long time. More precisely, this quantity here is precisely equal to one measure of operator entanglement for the unitary UT. So operator entanglement is just, well, it's just entanglement at the level of operator. Of course, by now, everybody here is familiar with the notion of entanglement at the level of quantum states. But of course, as soon as you have entanglement at the level of quantum state, you can lift that notion at the level of the operator space. Indeed, of course, the space of operators, we are in finite dimension here. I can endow that with the Hilbert-Schmidt scalar product that is denoted here. I remind you guys what the definition is of that, and the corresponding norm, Hilbert-Schmidt norm, just of course the square root of the Hilbert-Schmidt product of an operator times itself. And once you have that, the space of operators turns itself into a Hilbert space, and the operator space over a bipartite system is going to be itself a bipartite system. In other terms, the operator algebra over a tensor product is the tensor product of the corresponding operator algebras. In other terms, long story short, I can legitimately talk about entanglement if I have operators acting on a bipartite system. Operators themselves are living in some bipartite Hilbert-Schmidt Hilbert space. And so I can talk about entanglement, and I can in fact quantify that entanglement. This expression here that we obtain by hard averaging over local operators of the out of order correlation function turns out to be exactly that complexity measure for operators, namely the operator entanglement. That, by the way, has been recently shown one of the key resources or features, or if you wish, again, complexity measures that are making the, really making the simulation of quantum system hard from a classical point of view. And namely, it is precisely the kind of thing that a quantum computer will do better than any classical computer you can think of. But anyhow, that would be a bit of a digression. So the first point here, we can do the average of the OTOC, and this is the operator entanglement. And in order to give you guys a little bit of a feeling what this operator entanglement is, besides its, I would say, nearly obvious definition, let's consider a bipartite system that is symmetric, a balanced bipartition, namely dA is equal dB. I got two systems with the subsystem having the same dimension. And then in that case, you can show that operator entanglement is directly related to the entangling power of the unitary. What do I mean by that? Well, I mean something very specific. and namely given in a unitary U, the entangling power is defined, or at least the entangling power I'm talking about right here, is the average entanglement that is generated by U when it acts on R randomly distributed product states. If you do that, again, you end up finding a very nice, elegant formula that is connecting the operator entanglement G of U of T multiplied from the right by the swap operator between the two subsystems and minus the entanglement, the operator entanglement of the swap itself. And this formula here, the take-home message is simply that given the operator entanglement, there's a way to compute directly how much entanglement is generated on average by the operator starting from product states. Okay, this is a nice feature of that, but this holds true just for symmetric bipartition. Okay, let me move on. I'm going a little fast here, but again, if you guys have questions, feel free to stop anytime. Okay, so it turns out there's a big deal of information that is actually contained in the time behavior of this commutator, average commutator, or bipartite OTOC that I have defined and computed in general. And in fact, one way of seeing that is to consider the long-time dynamics of this quantity, namely the infinite time average. Of course, I'm working in a finite dimensional Hilbert space, so strictly speaking, no quantities they have long time limits. We have revivals and recurrences. Everything is going to be a quasi-periodic function. But of course, there's one way of making sense of long time limit, and as we all know, is to perform long time averages as denoted over here. And this is precisely what I'm going to do with my quantity. And again, the remarkable fact is that you can perform analytically in a fairly general setup this average here. So I have an explicit formula for the long time or infinite time average of the out of order correlation function. And this can be done analytically and is given by this formula here that, of course, it doesn't necessarily at first sight looks like the easiest thing in the universe, but in fact, there's a lot of structure in there. And in fact, it conveys quite a bit of information. And let me try to sort of spell out what is in this formula here. So assuming some non-resonance condition, what do I mean by that? I'm going to assume that and this holds generically, I'm going to assume that the Hamiltonian is not degenerate, and as well as the gap spectrum of the Hamiltonian is not degenerate itself. And if you do that, namely both energy levels and the energy gaps are non-degenerate, then you end up with this formula here that is in terms of the norms, of the two norms of some matrices. And these matrices here, which are defined over here, are just the, if you will, the gram matrices of the reduced density matrices of all the Hamiltonian eigenstates. In other terms, this formula here, somewhat unsurprisingly, if you wish, contains information about the spectrum of the Hamiltonian, as well as the eigenstates of the Hamiltonians as encoded by their reduced density matrix over system A and system B. In particular, you can show, and this is kind of a little calculation given this formula here that certainly requires much harder work to be obtained, that if you have, and again, let me focus for the sake of simplicity of the presentation simplicity, let me focus again on the symmetric case where the dimension of A is equal to the dimension of B, the two subsystems are the same size. And when the phi sub k, namely the eigenstates of the Hamiltonian generating the dynamics are maximally entangled across the bipartition AB, then you can explicitly compute this formula here and you get a little number that is this G maximally entangled NRC, and it's given by 1 minus 1 over D squared. What does it mean that? Well, it doesn't mean much unless you know that in fact the maximum available, you can prove the upper bound for this quantity here. This is one of the other results that we found. And the upper bound is given by the G max here, that is 1 minus over d squared, well, the minimum square, but here both the a and db are the same. So basically this d minimum square is just 1 minus over d. So you see that the time average for bipartite system, symmetric bipartite system, whose eigenstate, Hamiltonian eigenstates are maximally entangled, then this average, time average, is exponentially close, is big O, order of 1 over d, and here d is always the exponential in the number of, say, constituents of your system. Say, keep in mind for concreteness, if you wish, a bunch of qubits. So a qubit, say L qubits, so d would be like 2 to the power L. So if something is order 1 over d far from something else, we say that that is exponentially close in the system size. So this average here in this maximally entangled situation is exponentially close to the maximum possible available system, okay, value of this variable, of this quantity for this system here. And this also means that the fluctuations of this quantity here over time are necessarily very, very small. And the probability that you have larger fluctuations, just using some simple Markov inequality or something to that effect, the fluctuations away from this average value and from the maximum value are exponentially suppressed in the system, in the number of elements in your system and the size of your system. This means that this quantity here for a system that fulfills this NRC hypothesis over the spectrum and has very highly entangled state, you have a very high equilibration value and that the fluctuations beneath that equilibration value are very small. So this is one way, if you wish, in which you can clearly see that this quantity, at least its long time behavior, contains information about the sort of chaoticity that you have in your system, both in terms of the spectrum and the entanglement that you have in your system eigenstates. So it's a property of the full spectrum, the Hamiltonian, and the full system of eigenstates of the Hamiltonian. In fact, of course, you may wonder what happens if eigenstates are not all maximally entangled, say they are epsilon away from being maximally entangled, or if you wish, another way of saying that is that here I'm assuming that all the eigenstates fulfill a volume law, or strict volume law, but if they are just close to that, well, they still fulfill a volume law, possibly with a smaller coefficient, and they are epsilon away, then you can still show that the average of the out of order correlation function is very close to the maximum one. Okay, so insofar your system has an exponential, well, let me put it that way, insofar the number of states, of eigenstates of the Hamiltonian that breaks the volume law, so they have, for example, you have a massive quantum scar in the eigenstate system where many eigenstates that fulfill area laws, for example, if you had many Pauli localization or phenomena of that type, then you may have a violation of this. Then you may have a substantial decrease of the long time average of the out of order correlation function. But other than that, namely, if most of the states, if the fraction of states which violates volume law are in fact just exponentially small, then you have still that the average, the infinite time average is very close to the maximal one, and therefore fluctuations beneath that value are exponentially suppressed. So this is really a detector, this quantity here, therefore, in short, is really the long time behavior of this quantity here is really a detector of the level of chaoticity in terms of spectrum and entanglement property of the system eigenstates in your system. Okay, is there any question or comment so far? Okay. Okay, I think I'm
Actually,
going
sorry,
to...
excuse me.
Please.
Yeah, I have a question.
Please.
So, I mean, it sounds like what you mentioned, so this property that all eigenstates have volume law, that you would also have in an integrable system, right? So how, I mean...
Yeah, okay, this could be, but it's a good point, in fact. Well, you know, perhaps I should, let me do this. First, there are two ingredients here, I said. You have the NRC property, the degeneracy and the gap spectrum, and the volume law. If either one of these is violated, then you don't have this formula anymore, and you expect your time average being smaller. Okay, so there should be still a distinction regardless of the entanglement in the eigenstates. Let me show this. Actually, I was going to, for example, look this. Okay, you can prove a sequence of bounds on this long time average, and in particular, you can perform analytically the average, assuming that the evolution, the u of t through the dynamics, basically a random is a random sample over the group. Namely, you substitute the time average with the hard average, and you find the upper bound. Then slightly below that, there's the upper bound. There's the NRC average that I've just computed, and I have the analytical form. And then there's a slightly refined NRC assumption where you allow degeneracy, but not for the Hamiltonians, but not for the spectrum. And then all of these quantities here are upper bounds of the actual time average, G of t. Okay, so you can perform this, and of course we have done a bit of that in order to illustrate our theoretical results. You can, for example, consider here, I have a transverse field Eisen model on the left and a XXZ Heisenberg chain, and I can pick the parameter of each of the two models in such a way that the first one is going to be chaotic and the second one is integrable. And then if you see this plot here, well, of course, properly describing what is in the plot would take a bit of time, but let's say you can clearly see, so for example, that the exact chaotic behavior, this is the purple line, falls well below, and well, you know, it's below because there's a minus here in the, I'm plotting, in fact, minus G bar, is well below to the integrable one, okay? That is given the XXZ chain is the blue one. So here, the lower long time average for the integrable model is probably related, in fact, is almost certainly related to the existence of symmetries and degeneracy in the spectrum that are entailed by the symmetry group, by the integrability of the system. In fact, things are even worse for the integrable system TFIM, namely the transverse field Eisen model. And when you are in the integrable limit, you set H equal to 0. Of course, as we all know, you can map that into a system of free fermions. And if you have free fermions, you may have that the spectrum of the Hamiltonian is not degenerate, but there's no way that the gap spectrum is not. So in fact, the gap spectrum has massive degeneracies because on top of any state, if you add M free fermions, doesn't matter where you start, then your gap is going to be the same. And this massive exponential violation of the NRC, the non-resonance condition property, makes the integrable model described by free fermion much, much higher than the chaotic one. And even when you don't have free fermions, you have just integrability, then gap degeneracy or quasi-degeneracy in the spectrum makes the long time average smaller. So I would still argue that regardless of the entanglement of the system of eigenstates, the property of the spectrum itself make the long time average of this quantity different. Does this answer your question, at least partially?
It does, thank you.
Okay, thanks a lot.
And so just a quick
Please.
plot. So then do you be on the plot that you just had? So do you
okay, let me try, let me try to go back. I'm sorry about that. There's a huge delay here because I'm projecting things clearly in France. Give me 1 second, please. Go on.
Yes, so do you believe that there's a different scaling also here? I mean, are we supposed to see that like the red curve is, I don't know, logarithmic and the purple one is something else?
Look. I like the way you phrase your question. Would you like us to think? Let's say that you see, yes, I would like you to think that, but then if you guys were to ask me, okay, please provide conclusive evidence for that, I would say I don't have it yet, okay? This is what we believe is the case, and we believe that indeed the long time behavior of this quantity here in terms of scaling is precisely what would allow you to tell chaotic models apart from integrable models. But whether I have sufficient evidence for that numerical or even theoretical, I would say we're not there yet. So it's a great question that I don't have the answer to.
Okay, thanks.
But I believe so.
Yep, thank you.
Okay, thank you. That was a good one. You see, I just go to up 10 spins, and that's the problem. Of course, these are quite massive simulations that in this paper here, were mostly aimed just to illustrate the theoretical results. Much more careful and thorough and systematic state-of-the-art numerical calculation are underway to answer your question. So perhaps next question. Okay, how much time do I have left?
Exactly 10 minutes left, including questions.
Including questions. Well, I had a few already. So let me now share another couple of results that are providing us with a further physical and I would say operational interpretation of what this average OTOC would be. Okay, so given the system, given the dynamics U of t, I can always build in a bipartition. I can always build the quantum channel. A quantum channel, well, is what we quantum information people consider, well, the only legit quantum operations and quantum transformations. We believe that the most general type of quantum dynamics that is allowed in nature, insofar nature abides to quantum theory, is provided by a completely positive map. And one way of building that is the following. You take subsystem A and you prepare subsystem A in some state rho A, say later on is going to be a pure state. But at the same time, you completely randomize the complementary system B. So you have an initial state that is going to be a tensor product of rho A times the fully chaotic state, namely the normalized identity, the maximally random state over the system B. It's like I'm just doing some local cooling, so I can prepare some state with non-zero, with less than a maximal entropy over A, while I keep at infinite temperature the subsystem B, and then I let the system evolve. And then I take the trace over B. Of course, I could do the other way around. I could prepare a state, say a cold, cool state in B and a completely random infinite temperature state in A and let them evolve and taking the trace over A. In this way, I have defined two quantum channels that I denote by lambda t of A and B in this way. And these channels here, if you were a non-scrambling map, say a bipartite, a pure product, if no interaction between system A and system B, this would just give you basically the entropy of system rho A, okay? Because they would completely factorize and the identity, the infinite temperature state is always gonna be a fixed point of any unitary evolution. So at the end of the day, the entropy you put in is what you get out. On the other hand, if you have a true scrambling dynamics, what the information that was locally encoded in the cold state A gets spread across system B or vice versa. The mass that was initially stored, the infinite temperature mass that was stored in system B now spread across the boundary and infects and increases the entropy of system A. Either way, you can define the linear entropy of a state that is defined 1 minus the purity, and this is the entanglement measure that I was implicitly using even to define what operator entanglement is. But of course, you can do that at the quantum state level as well. And this is the linear entropy. So it turns out, and again, this is kind of a little work here that is conceptually quite satisfactory, I would say, or I believe it is, that the G of t is really, other than some prefactor, is the average entropy production measured by the linear entropy is the, let me say in this way, is the average linear entropy production by this channel when you start off from a pure state in system A. And this is exactly what this formula here is meant to say. You start from a pure state in system A, you act on with a random hard unitary over it, namely you produce a random state psi, you tensorize with a completely mixed state over the system B, you let the system evolve with your dynamics U of t, unitary dynamics U of t, you trace over B, and you get this channel. The higher is the entropy of this channel, the average entropy of this channel, the higher is G of t. This gives to G of t of this commutator here a very physical, I hope you guys will agree with that, a very physical, intuitive, as well as operational meaning, because in fact, in words, I've just described to you guys a protocol how to measure that, right? And in fact, it could even be something, well, perhaps not right now, but not far in the future. I believe this is a kind of experiment that you can actually do because, well, the linear entropy is in fact a measurable quantity as soon as you realize that the purity of a state is just the expectation value of the swap operator times the second tensor power of the state itself. You take the two copies of the state row, and then you measure in that quantum state the expectation value of the swap operator, that of course is also an Hermitian operator, therefore is unobservable. And in fact, people have done experiments along those lines, though probably not at the level of complexity that would be required in this particular instance here. So operationally, this out of order correlation function is just, and really, I think, it makes justice to the idea that scrambling is somehow related to entropy production. This is precisely the entropy production you get on average if you start from some local stuff that is pure, that is surrounded by a sea of infinite temperature mass, and then you let the system evolve, and how much entropy is produced on average. This is precisely the scrambling measure that we have. Okay, so this is one result that we're kind of proud of. And because of the operational interpretation, and well, you know, we quantum information people will like that. And let me perhaps share with you guys the last thing, that of course this is really like a quantum information-y kind of thing to do, but there's yet another very interesting, I would argue, operational and physical, and in fact, as you're gonna see momentarily, geometrical interpretation of this quantity here. Indeed, it turns out that the bipartite OTOC is a geometrical quantity. Indeed, it quantifies the distance between this channel here and the depolarizing channel. Okay, we have quantum channels. They're linear operations over Hilbert spaces. We can define a metric structure over that space. And we can define what is the distance between two channels, and this distance here is in information theoretic one, namely the larger is the distance, the harder is going to be to tell these two quantum channels apart with any protocol you can come up with. And in particular, this quantity is telling you the distance between the depolarizing channel that is defined over here. It just takes an input state rho A and it spits out the fully random state, is something taking any state to the maximally mixed state, and my state here, and my channel here. So basically you see the formula down here, and I'm sorry because again I keep not seeing my pointer, so I really have no idea what I'm pointing at. But G of t is the maximum possible value that I've already told you, that is 1 minus the dimension square, as it should, minus the dimension, minus the distance between these two channels. How do I define the distance between these two channels? So really is the how far is my scrambling channel, rho A and rho B, from the fully depolarizing one. You would agree that the fully depolarizing one is the maximally chaotic channel. Whatever gets in spits out something that is totally random. And how far is my scrambling channel from that is precisely a measure, or it's directly related to the value of the OTOC. So let me just remind you how we measure quantum information distance between quantum channels, namely between completely positive maps. Well, we know how to measure the distance between quantum states. And so what we do, we resort to the so-called Jamelkowski isomorphism, namely we're mapping channels to states using this formula over here, giving any channel epsilon. You can define a corresponding bipartite state rho epsilon in this way over here, acting on a suitable maximally entangled state. And this is an isomorphism. You map channels to state, and then whatever you say about those states is actually a statement about the channels. And in this way here, I can define this formula here. That is another very nice geometrical interpretation of the OTOCs in terms of the operational, informational distinguishability between the scrambling channels that are generated by your Hamiltonian and the totally depolarizing channel. Okay, I think I'll stop it here. I would have a whole bunch of other slides, but of course, I'm running late of time. So maybe now I go back and somehow I had the summary at the beginning. So in our work, what I've shown that I can define a bipartite OTOC averaging the commutators between two unitaries, one of which has been time evolved over the full Haar group. And I find that this average, in fact, is exactly a complexity measure for operators, where the operators, of course, here is the dynamics itself, is U of t. And namely, we could establish a rigorous connection between operator entanglement and in turn to entangling power of the dynamics and the OTOC. The third result is that in the long time limit, by performing time averages, we can connect this long time average value with the structure of the Hamiltonian spectrum, and very interestingly, I believe, with the structure, the entanglement structure of the full eigenstates of the eigenstate system of the Hamiltonian. Again, you've got many-body localization of some massive many-body quantum scar in the system that would be detected by the long time average of this quantity. Finally, scrambling of local information very satisfactorily for a quantum information person is really a quantum information distance between quantum channels. The scrambling quantum channels defined by the unitary itself and the maximally depolarizing channel in the system. Okay, this is what I did. We have a few related works here, just a little list. We can extend that in several ways. Of course, the most natural question you can ask is what happens if you move from unitary dynamics, namely closed quantum system, you move to open quantum system? Well, you can do stuff, and we in fact done at least a bit of it, and it's been published over here in the paper number 1. You can extend that massively to the situation where you're not just mixing up local operators over A and operators over B, but you take a general algebra of operators in the space and you scramble that, comparing that with the commutant of this algebra. Namely, I can extend this formalism here, the average OTOC formalism, to general quantum algebras. You can connect to quantum coherence, and you can also talk about finite temperature. But that's all I wanted to say. So thank you very much for listening, and I'm sorry for being the least and the last. Okay, thanks a lot.
Yeah, thanks for your talk.
Thank you.
We already had a bunch of questions, so if there is one short question, maybe.
Hello, Paolo.
Perhaps Hubert.
Yeah,
Hubert said that
thank you for
he
this.
feels compelled to ask us.
No. Thank you for this overwhelming talk. So you had these inequalities between the G functions depending on the averaging procedure. Can you make them strict inequalities? What do you think?
Well, of course.
I mean, in other words, is the average
the upper one? Yeah, of course. It's a perfectly legit question. In fact, it's an intelligent question, Hubert. I didn't expect any less from you, of course. So G-har, the first one, of course, is very, well, that is not really, you can get exponentially close, and I would take that as the definition of what a chaotic system is, right? Or one possible take of what chaoticity means at the many-body level, namely when the average of the OTOC gets exponentially close to the one that you would obtain from a completely random unitary, okay? The question is more like whether NRC and G, for example, say the average NRC and the GT, the normal one, where I just do numerically the average, whether they are close or not. And in fact, the answer is if the system is obvious in some sense. If the system fulfills the NRC assumption, and most of them really do. A generic Hamiltonian that you were to draw randomly out of the space of Hamiltonian would fulfill the non-degeneracy of the spectrum as well as the non-degeneracy of the gaps. Okay, in that case, this equality is saturated. Is exactly true. Other systems, they are just close to that. For example, if you look at the picture, you see that. Let's see over here. The yellow NRC plus integrable and this orange and the exact integrable, they're very far from each other, because this is telling you that, well, very far, they are apart. This means that, of course, the integrable doesn't fulfill NRC. But for example, I have the blue one you see, NRC plus, whatever that means, integrable XX Z chain, and I don't have the sort of the real time average, is because in that case, the real time average really performed numerically by exact diagonalization and performing the time average numerically is basically indistinguishable numerical from the one that I obtain analytically with NRC plus. So the answer is for a generic system, I expect those equality being saturated, and for many systems having small violations. Of course, the more structured, the richer is the structure of the spectrum of your Hamiltonian, or more peculiar is the quantity of entanglement that you have in your, well, let's forget about entanglement. Let's say the spectral features. If they are far from that, and this happens in integrable system, and in particular in integrable system that are, well, mapped into free fermions, then these are not saturated. And in fact, there's some gap, there's some daylight between these two. Between the predictions of the analytical formula and the actual time average.
All right. Well, that's a thorough and clear answer.
Does this answer your question?
Absolutely.
Partially?
Thank you, Pablo. So let's thank the speaker again. And I think I'll conclude the meeting with a few people who are left. And I want to thank everybody online for having been there all this time faithfully. Thank you, everybody who's here. Thank you to the organizers. And I'd say let's go home and have a big fat drink. Okay. Thank you.